This lesson deals with supplemental problems and solutions. In the ECE201 ebook, for each chapter of lecture notes, there's a section labeled Supplemental Problems and Solutions. These are a collection of former homework problems with their solution, or a write-up of an application that uses some of the ideas that we've discussed in the course. This one is Supplemental Problem 1.1, as the beginning of that section of supplemental problems. Suppose that I have a current through a circuit element that's a constant 20 milliamps. If the charge on one electron is 1.6 times 10 to the minus 19th coulombs, then there are 1 over 1.6 times 10 to the minus 19th electrons in 1 coulomb of charge. And of course, this is a very large number. We find the total charge and the number of electrons transferred during an interval of 1 microsecond. In the course notes, we said that current was related to the derivative of charge per unit time. To be able to calculate a change in charge, we would need to solve this equation for Q. Let's integrate both sides of the equation, dt. Get a cancellation of the dt's here, and so if we take the integral of 1 dq, that's just simply the upper limit minus the lower limit. This would be the change in charge that's transferred between a time interval t0 and t1. So let's take an integral then from 0 to 1 microsecond of the current, which is constant 20 milliamps as stated in the problem. And that would give us 20 milli times the integral of 1 dt, which would be 1 microsecond minus 0. Now milli is 10 to the minus 3, and micro is 10 to the minus 6th. So the product of those two would give me 10 to the minus 9th. So I have 20 times 10 to the minus 9th coulombs, but in our chart of prefixes, 10 to the minus 9 is nano. Okay, so the number of electrons then would be the number of electrons per coulomb of charge, which was calculated above as 6.25 times 10 to the 18th. And if we multiply that by 20 nanocoulombs, then the coulomb unit cancels. And I've got 6.25 times 20, which is 125. 10 to the 18th times 10 to the minus 9th is 10 to the 9th. Now normally I'd put the unit here of giga, say I have 125 gig electrons, but most scientists don't talk that way, so I'm just going to leave it as 125 times 10 to the 9th electrons. But in general, in the course, I want to put all answers in engineering notation with the appropriate units. So in this case, the 10 to the 9th will be replaced by giga. There was a footnote earlier in the problem. What we've got here is calculation for the change in charge, but I could calculate the charge transferred at a time t1 in terms of an initial value plus the integral over that change in time. This would be called an initial condition. Again, we talked about those kind of things in calculus. This is really calculating the charge transfer at a time in the future. Some people just don't want to use a subscripted variable on that. You could just simply call that Q of t. Maybe replacing t1 by t. But since we were integrating with respect to t here, we really shouldn't use the same letter. It actually means something quite different. So let's just use a dummy variable here, say x. And then when we evaluate the upper limit, we'll have the answer in terms of t. This is just doing a change of variable. At the end of supplemental problem 1.1. In the index for the ebook, you'll see that there's a section that labels the supplemental problems back to the lecture notes themselves. So whenever we cover a particular page in the lecture notes for that chapter, there are problems that you could then do. It is simply practiced as more examples of using the ideas in the e-notes.